So starting off with this session, bioenergy conversion technology and scale. Get the laser pointer mode. We'll have a quick look at procedures for technology selection, as you may have, as you may remember, there are quite a few different options for technology when it comes to bioenergy. We'll have a quick recap of what we saw from the earlier sessions. We'll have a look at different scales and the efficiency of different systems. We'll look at the scaling of some critical system components. Look at the space requirements. And if there's some time left, we'll have a quick look at some startup technical modeling that can be used in say setting up the overall model for feasibility analysis. So the overall objective of this session is to discuss how to select technology for bioenergy conversion, and to work on some scaling of systems and project components. So what we looked at in one of the previous sessions on conversion options for bioenergy was that, say, starting from the different types of biomass, and after harvesting and collection and provision to the project site, we have different options for converting the biomass to energy. On one hand, we have thermochemical conversion, which includes combustion, which includes pyrolysis, either fast pyrolysis yielding liquid products, or slow pyrolysis yielding solids, charcoal. We have gasification, solid biomass gasification, resulting in a gaseous intermediate product. On the other hand, we have physical chemical conversion options, extraction of oils, and the transesterification of vegetable oils, which will both yield liquid biofuels, which can then be converted to use for energy. And we have biochemical conversions, and that includes fermentation, alcoholic fermentation yielding liquid, anaerobic fermentation yielding biogas, and there's, in principle, there's composting, which produces heat. Now, depending on the type of intermediary product, it can be converted to power and heat. Now, what we'll be looking at particularly are systems typically used for, let's say, larger scale production of electricity and/or heat. And it includes the combustion route. So let's say from solid biofuel combustion to power and/or heat. There's a gasification route, producing producer gas, which can be used in an internal combustion engine for the production of power and heat, and biogas production through anaerobic fermentation of wet biomass, resulting in the production of methane, so the methane component in biogas, which can also be used as a generator fuel for production of electricity and heat. Different conversion options. We have biomass combustion and steam cycle, which can include a steam turbine or a steam engine. Capacity range for steam turbines is roughly, say, upwards from 500 kilowatts. Steam engines are smaller, from, let's say, roughly 20 to 50 kilowatts upwards to 1 or 2 megawatts. The efficiency depends on the scale and the project setup. So let's say whether that's production of electricity only or production of electricity and heat. Let's say for smaller turbine systems, you could have an efficiency of roughly 15% for a 1 megawatt unit, and that can go up to about say 35% for a large scale unit. But if you would have combined heat and power, you would produce steam at a certain pressure and temperature, and that means that you have somewhat less energy converted to electricity, so the efficiency on electricity will be somewhat lower. Specific advantages: technology is quite robust and reliable and mature. It's suitable for a very wide range of types of biomass. It's basically combustion in boiler furnaces, and well, there's no real limit to the type of biomass that can be used. And if you produce both heat and power, you can have a quite high efficiency. Specific disadvantages are the higher investment costs and the say somewhat lower efficiency if you look at the smaller capacity systems. Looking at gasification, in combination with an internal combustion engine, that's applicable from smaller scales upwards. You see that the efficiency is already at a higher level in comparison to steam systems at a much lower system capacity, and can similarly go up to let's say it says 35%. That might be on the high side because of the internal combustion engine efficiency. Critical points are gas cleaning, making sure that the producer gas is free of tar and dust in order to avoid any damage to the engine in which the gas is used. And the technology is very sensitive to the specification of fuel, particularly size, morphology, moisture content, the ash content, and say the overall composition, the mixing of different types of biomass. Biogas production through anaerobic digestion, also using internal combustion engine as a means of converting the chemical energy in the biogas to electricity and heat. This is also mature technology. Can be applied at a quite large scale range. It can in principle be applied at scales smaller than this 50 kilowatts, although you won't really see them at that small scale range very often. The conversion rate very much depends on the type of feedstock, the system scale, and the loading rate of the system. And very critical here is also the gas cleaning biogas, removing components that could cause damage to the combustion engine, particularly H2S. Like I said, it has a quite large scale range, although the larger scale is let's say this 10 megawatts would be more applicable to so-called green gas applications, where the gas is upgraded and injected into natural gas networks, and to some extent let's say systems, let's say industrial systems where very large quantities of waste are produced. Further advantages are the reduction of methane emissions, methane being a very strong greenhouse gas, and by capturing methane, by using the emission to the atmosphere, there are very large advantages for reduction of the greenhouse effect. The effluents from biogas production, furthermore, that's liquid or solid, can still contain very high quantities of plant nutrients. So they're very often used as fertilizer in agriculture. Some disadvantages are the relatively high investment costs, very much depending, I should add, to the system setup, and the generator maintenance, especially for systems that make long hours grid connected. They really need very frequent and heavy maintenance to extend their lifetime. We've been looking at different types of biomass feedstocks from different sources: forestry, agriculture, industry, and households. What we see is different types of biomass from different types of sources. We have a class of lignocellulosic biomass, which includes, which is more or less, let's say, the solid types of biomass, like wood, like stalks, husk, shell. With biomass, which is let's say oil, sugar, or starch containing, which can be used for the production of plant oils, or biodiesel, or ethanol fuels. Examples are sugarcane, but also sugarcane molasses, for example, cassava residues from starch production. Talking about palm oil, talking about waste oils. We have livestock wastes, for example, manure, slaughterhouse wastes, which can be converted to energy, usually by anaerobic digestion. Combustion is also an option. And we have other types of organic waste, including the organic substance in the municipal waste, different types of wastewaters and sludges. Important properties of feedstocks are, let's say, the moisture content, the calorific value, ash content, and the size and shape of the biomass, which we call morphology. When we look at biogas production, we look also at let's say the dry matter and the organic compound, and the organic part of the dry matter. We look at the methane production potential. We look at the presence of nutrients like nitrogen, but also potassium and other nutrients. We look at wastewaters. We look at the chemical oxygen demand, the biological oxygen demand, which are indicators of the quantities of organic solids in the wastewater. When talking about feedstocks, we talk about available quantities, which can be used for energy production, and that can be, let's say, in the first instance, those can be waste and byproducts from different sources. It's also possible to produce your feedstocks for energy production, like energy plantations, like wood or fast-growing wood types for combustion, but also like energy maize or other types of energy that can be used for biogas production. What's important is the extent to which existing resources are already being utilized for any purposes. So that might mean that the actually available quantities are more limited to what is being produced. And what's important is the fluctuation in the availability. And thirdly, what's important is the logistics of getting the biomass from where it's produced or where it's available to where it can be converted to energy. I think I'll skip this one. Energy demand. I think that's for energy professionals. That's a bit known already. So technology selection is indicated. There's different options, and what you do is usually you look at what is available in terms of biomass. What are the properties? Because every technology has a certain requirements with respect to feedstock to which it can be applied. So, as I said, combustion is a bit more versatile. Where it comes to solid biomass, at least, we look at the scale. Each technology has a certain application scale. Some can be used at relatively small scales, but then maybe not up to the very large scales, and others start being feasible from larger scales upwards. We look at the characteristics of the energy demands, because some technologies are more suited for supplying energy in say dynamic load conditions, very high fluctuating electric loads in industry, for example, some industries. And a fourth potential selection criterion could be the complexity. So the operation and maintenance of certain technologies is more complicated and requires, let's say, a higher skilled technical staff than others. I should add this also relates to maybe the scale of operations. So larger scale systems tend to be a bit more complex, and that adds to the need for higher skilled technical staff. So looking at the first criterion, the biomass properties, very generally speaking, you could say that solid biomass is usually more suitable for thermochemical conversion, like combustion and gasification, and in principle also pyrolysis. And then if we say solid biomass, actually what we mean also is lignocellulosic types of biomass, like woody biomass, like husk, shells, whereas types of biomass containing large quantities of water, easily degradable types of biomass are more suitable for anaerobic digestion. We're usually looking at biomass in the form of, from water, which is very liquid, of course, to sludges, to materials that can have, let's say, up to 20 to 25-30% of dry matter. Let's say upwards from about 70% of water. What we can also say is that there's an overlap, a large overlap between gasification and combustion. In general, gasifiers are a bit more picky when it comes to the type of feedstock. And what you can say is that what can be gasified and can also be combusted, but not necessarily what can be combusted can be gasified. I should also add perhaps that, you know, let's say the novel technologies, gasification technologies, for example, you may also find gasifiers that actually work with very high water content feedstocks, but that is, let's say, not commercial technology yet. Now, what we see here on the left-hand side and in the middle is more or less what we saw earlier. What we see on the right-hand side is more or less the conversion type that can be considered. Here on the top, you'll find the let's say the solid types of biomass, which are all suitable for combustion. You'll also see in some cases that types of livestock waste are combusted, and then we're talking about, for example, chicken dung, which is quite solid and stackable. We see that some types of biomass are quite suitable for gasification, and some are in principle suitable for gasification under certain conditions, like particular types of food waste, like residues like bagasse, crop residues like stalks and straw, and here also some types of livestock waste are actually used for gasification systems. And then, let's say, in the lower part of the list, you'll find the feedstocks that are more usually applied to anaerobic digestion, like wastewaters, the organic component of municipal waste. Livestock waste is a very important type. Organic waste is a bit of a container type that includes different types of wet organic waste produced from different sources, and also crop residues, depending on technology, can be used for biogas production. So this is more or less a figure that can be used to orient yourself. You're faced with particular types of feedstock. You can have a first indication of the indicative conversion technology options. What is important is that you actually start looking also for specific experiences with different types of feedstock. Let's say looking at literature, looking at different sources you can find on the internet, for example, and start really thinking in a certain direction. Also to start talking with suppliers of different types of bioenergy technologies to discuss if their systems are actually suited for the type of biomass that you want to work with. The second point was scale. Scale is, let's say, more or less set by, on the one hand, the energy demand. Say, if there's a certain limitation to the amount of energy that can be produced from the demand side, then that sets a certain maximum to the production scale. On the other hand, there may be a limitation to the amount of biomass that is available, and there may be certain, usually minimum scales that can be considered from an economic point of view. In general, this figure should be, you know, considered as indicative. Say applicable scale ranges for steam turbine systems start from, let's say, somewhere between 100 kilowatts and 1 megawatt. Smaller systems can be applicable with usually in industry in CHP applications. So where say back pressure turbine systems where the steam is still being used in industry. So it's one of the things that we saw in the Maragra sugar factory system, that there was quite a range of turbines, let's say smaller scale turbines being used for direct drive of some of the equipment. And those were smaller turbines with say steam outlet pressures that were still applicable for satisfying steam needs in the sugar factory. And of course, it goes up to say above 100 megawatts, let's say to the hundreds of megawatt scale. Although there you typically go into the let's say the large scale power plants, which are usually, so when discussing solid fuels, are usually coal and or it's a coal in combination with biomass. Biomass only plants usually don't really go up much higher than 100 megawatts. Steam engines, on the other hand, are suitable for, let's say, smaller applications, let's say below 100 kilowatts, and let's say typically up to a few hundred kilowatts, although larger systems are available and that are being applied as well. So there's a certain overlap where you can, you know, in principle, consider both steam engines and steam turbines. Gasification systems for the smaller ones, you'll find them well below, let's say, 100 kilowatts. It's typically fixed bed gasification, which are found in quite large numbers around the world, and those systems generally go up to roughly one megawatt. Although, let's say, larger projects can be conceived by having multiple large fixed bed systems working in parallel. We have fluidized bed systems for gasification, which start from just below 1 megawatt up to, let's say, 10 to, let's say, 50 megawatt scale. So we have to try and mute someone. So Manuel, can you please mute?
Bart, maybe you make me co-host so I can help you on.
Yeah, just please. I need to fine-tune the lists. Right. Okay. Thanks.
Yes. Thank you very much.
Okay. And let's say biogas systems, as indicated, they can really go down to very small scales. Although in practice, you'll find them from, let's say, 20 to 50 kilowatts upwards. They go, let's say larger scales are usually found between, let's say, roughly let's say a few hundred kilowatts up to a few megawatts. I think most of the larger farm scale units and then larger industrial units are found in that scale range. So the third point was the energy demand characteristics. What is optimal for bioenergy systems? I think that's especially from an economic point of view that goes for any energy system. So if you have a constant high loading rate, so let's say that's something that you typically find in grid connected systems where they can operate at let's say more than 90% of their capacity, and let's say have a continuous production of energy. But of course, that's not always possible, particularly in off-grid situations, and especially in let's say industrial power plants. You will have fluctuations in energy demand. So it means that you always have to be able to supply even the peak loads. That means that average loads will be lower than the optimal operating point of systems. Especially when you look at internal combustion engines, particularly gas engines, but also diesel engines running, for example, on vegetable oils. You will see that when you operate them at a lower loading rate, you will have lower efficiency, and this is particularly true for let's say spark plug engines. So gas engines, they have a more or less linear efficiency to loading rates. Well, let's say they're more or less linear. In general, for most of the systems, you can say that a loading rate of at least 50% should be strived for. That's both for engines, but also for turbines, for example. And what is important to know is that the gasifiers are not so very suitable for, let's say, very low loads. So less than roughly 30% usually, or highly dynamic loads for very large load fluctuations. Fourth point, complexity. As indicated, this is a bit related to scale and to the type of application. Generally, you could say that large boilers and steam turbines and larger gasifiers should be considered maybe, let's say, industrial installations, and they also need, let's say, industrial type of operation and maintenance staff and strategies. Looking at smaller boilers and steam engines, for example, and to some extent also smaller gasifiers, you might also consider, say, smaller and rural type of industrial settings. And looking at biogas systems, to some extent also small gasifiers, you can consider, let's say, farm type of operations, and then small rural industrial settings. What I'm going to do right now, I prepared some small polls to see how that works. I'm going to ask you all to participate in this. I'm going to ask you the question: what the typical technology options would be for a 3 megawatt grid-connected power plant running on wood chips. Let me see if I can start that poll. I hope you see it now. You can make a selection, and there's only one of the answers is correct. So that's the question. What are the typical technology options for a 3 megawatts grid-connected power plant running on wood chips? Is that option A, steam turbine? Option B, steam turbine or gasification? Option C, steam engine or gasification? Or option D, option 4, steam engine or biogas, anaerobic digestion? So maybe if you take a minute to think about this and then give your answer. If there's any questions about this, please don't hesitate to ask. I have 4 answers. I hope we can get a few more. No, nothing more? Okay. Well, we have 4 answers. We have hold on. There's a 5th. Two persons indicating steam turbine, and we have one who says steam turbine and gasification, one who says steam engine or gasification. We have steam engine or biogas. Okay, I'm closing the poll right now. Thank you. So 3 megawatts grid connected, running on wood chips. Well, let's have a look. What can we think about? We have wood chips. So what are the options with wood chips? Basically, with wood chips, we have thermochemical conversion. So that's let's say combustion and gasification. With combustion, we can go both to steam engine or steam turbine. We have a 3 megawatt system, which is, you know, more or less here in this range here. Well, of course, turbine this is a pretty good scale for a turbine, even though the overall efficiency of the system might be still be limited, might still be below 20%, for example. 3 megawatt for steam engines would be a bit big. Would probably need multiple steam engines, and the efficiency of steam engines would most likely be substantially lower than that of a steam turbine. So let's say for the combustion options, I would say the turbine would be the technology of choice. Yeah, and secondly, gasification would also be a possibility. Let's say fluidized bed gasification would be at this scale would be appropriate. Although it's also possible to use different fixed bed gasifications running simultaneously in parallel to add up to 3 megawatts. So basically, the right answer would be steam turbine or gasification. So we have a second poll. Let's say can always try again. And it's for a 150 kilowatt off-grid power plant running on coconut shell. I will start again the poll. So what are the options for a 150 kilowatts off-grid power plant running on coconut shell? Is that gasification? Is that gasification or steam engine? Is that gasification, steam engine, or steam turbine? Or can it be steam engine or anaerobic digestion? The poll is opened. You're welcome to cast your vote. I have only one vote so far. Yeah, number 2. I hope to get at least 5 again, like with the previous case. Just to be clear, if I say, let's say, gasification or steam engine, I mean that both options are open. When I say gasification, steam engine, or steam turbine, I mean that's, you know, all 3 options are possible, are open. Steam engine, biogas can be both. And what may be important is to emphasize that the biogas, I mean the gas produced with anaerobic digestion. And gasification is the thermochemical conversion technology.
There is life after this place. Existe uma vida depois desta terra. Ladies and
Okay. Well, we have 5 votes, so let's have a look. See, in the poll text I had 100 kilowatts, and in the presentation text I had 150. For the outcome, it doesn't really make a big difference. Let's have a look. Let's go back to where we were. We're talking about coconut shell, which is let's say a solid lignocellulosic type of biomass, which would fall in this category. So basically, you'd have combustion or gasification as main conversion routes. We're talking about, let's say, 100 or 150 kilowatts. That means that we're sort of in this range, which would be usually too small for a turbine system. Say, unless again you'd have a very specific situation in which you could apply, for example, a back pressure turbine producing process heat for an industry and have electricity more or less as a secondary product. So you'd be most likely looking at let's say either a combustion and steam engine type or a gasification conversion, and anaerobic digestion is more suitable for biodegradable, easily biodegradable types of biomass, and that would not be specifically the case for coconut shell. So that would be the answer. That would be answer B, gasification or steam engine. And so looking at it further, but maybe I'm getting ahead of myself. Gasification would have a substantially higher potential efficiency than a steam engine at this scale. We resume with aspects of scale and efficiency. Scale, as you can imagine, is essential. Getting the right system scale, because a too large system will be more expensive than a smaller system, and still more or less produce the same amount of energy, if that's the limiting factor. On the other hand, that is quite specific for some types of bioenergy systems. Large scale that will run at a low loading rate can have a low efficiency. So that means that let's say choosing a better scale can actually have benefits in terms of conversion efficiency, and let's say from the same amount of bioenergy, you could, from the same amount of biomass feedstock, you could produce more energy if you have the appropriate scale. And also some systems, particularly gasifier systems, for example, but also boilers, they can have operational problems when they are run at a very low loading rate. At the same time, of course, a too small scale would not be right if certain demand has to be covered. For example, in an isolated supply system situation, And it could be economic if a system is too small to be financially feasible for example, for a grid-connected system. Now the capacity, as we've seen earlier, is mainly based on the energy demand, for example, in industry or for a mini grid. Resource availability, which is usually the limiting factor in, let's say, grid-connected systems, and technology aspects, for example, the conversion rate of biomass to energy. What we see in grid-connected systems is generally higher loading rates. Say 90% would be a good target, and continuous operation. Say apart from incidental stops for maintenance. We see a scale which is mainly determined by resource availability, or the let's say the possibility of producing quantities of biomass. For example, in cases when the biomass feedstock is being produced in plantations. For isolated systems, you can have certain ranges of appropriate scale, which is set by peak load and by base load. For example, if you want to make sure that your capacity is always sufficient, then you may choose for a system which is a slightly higher capacity than the maximum expected peak load. For example, if you make sure that the maximum expected peak load is no more than 80% of the system capacity. On the other hand, if you want to have a system that always runs at least 30%, then you can set a certain maximum capacity so that the system will never run at less than, for example, this 30% of its capacity. And options to avoid the minimum and maximum requirements are to have multiple units, let's say running in parallel, or let's say running in turn intermittently. For example, if you could have a certain isolated system in which you could have a very low base load, you could cover that by a smaller generator. And if you have, for example, in daytime and evening, you have higher loads, you could run a second generator, so a larger generator, in parallel, so that the load better matches. So the generator capacity better matches the occurring loads during, let's say, all circumstances. Now, efficiency, conversion efficiency, it's an important aspect for determining the amount of energy that you can produce from a certain quantity of biomass feedstock, or for determining the amount of biomass feedstock that is needed to satisfy a certain energy amount. It's mainly based on, let's say, the type of technology and the scale. At least the maximum attainable efficiency is mainly based on technology and scale. but the actual efficiency that you will find at any moment in time can also be determined by the operational aspects. For example, the system loading rate is one of those aspects. It's indicated, especially the efficiency of internal combustion engines is very much subject to loading rate. But also the state of maintenance of equipment, for example, can be determining for the actual efficiency of a system. And what is important to realize is that, especially because of the system loading rate, you can have a system loading rate which can vary throughout the day. You can have varying efficiency during the day. For example, you have a single generator which at some points can run only at 20-25% of its capacity. And you have a much lower efficiency at that time than maybe later on in the day when the load is double and the system can run at 50% of its rated capacity. Now, for the three different types of systems that we've been looking at, we can look at the efficiencies that play a part. So the part efficiencies that play a part in the overall efficiency. For combustion and steam systems, say the overall gross efficiency depends on the boiler efficiency on one hand, so the efficiency of converting the fuel to heat, and let's say the heat to steam. Then we have the turbine efficiency, which is, let's say, the extent to which the turbine can convert the heat in the steam to mechanical power, shaft power. And then we have the alternator efficiency. That should also include the let's say the gearbox. So let's say between the turbine shaft and the alternator terminals, you'll have a certain efficiency, which is usually in the order of 95%. Turbine efficiency is, of course, dependent on the steam conditions. So we have high pressure steam on the inlet and very low steam pressure on the turbine outlet. Then we have it's a higher efficiency than when you have, for example, a back pressure turbine which expands to a certain intermediate pressure steam. Looking at a gasification system, the overall efficiency mainly depends on the gasifier efficiency and the generator efficiency. The gasifier efficiency very much depends on the scale, on the technology. A very typical range would be, let's say, 60 to 80%. For let's say a large scale fluidized bed systems, you could have higher efficiencies, 85 and even a bit above 85%. For very small systems, you could have efficiencies below 60%. Gas generator efficiencies are usually in the range of 25 to 40%. Also, you can have a little bit higher, a few percent points, or a little bit lower even. But what you see is that at lower loading rates, it can really be substantially lower. So if it's running at only 50%, then the actual efficiency can be more in the range of, let's say, 10 to 20%. This also goes for gas generators used for biogas systems. What is a bit tricky here is that you typically look at the conversion from gas to electricity. And of course, in an aerobic digestion system, you also have the conversion of feedstock to gas. But there you wouldn't really talk about certain efficiency. You'd rather be looking at, for example, determining factors like the retention time of the biogas system, the digester system. You would be looking at the methane production potential of the feedstock in combination with the typical methane percentage of the biogas. So it's a bit different than from what you would usually see in the efficiency factors in thermochemical conversion systems. Looking at specific systems, steam engines, they usually have operate in back pressure, so without condensers, and that means that automatically you get a somewhat limited conversion efficiency. You also see that with back pressure turbines. You could easily lose, let's say, 50% of your efficiency if you don't expand to sub-atmospheric pressures, say at pressures below one bar absolute. You have a relatively small scale, also in comparison to turbines, so it means that the isentropic efficiency of the whole system is by default a bit more limited than, let's say, larger scale, highly optimized turbine systems. What you will see in practice usually for steam engine systems is an overall efficiency which is in the range of, let's say, 5 to 10%. The advantage of, let's say, good steam engines is that the efficiency is quite constant. At loading rates from about 50% upwards. In contrast, for example, to internal combustion engines. What you see with steam turbines is that you have a very large range of different steam conditions, and both on the high pressure side and on the low pressure side, depending on what kind of energy demand needs to be met, whether it's just electricity or also heat. For larger systems, you can get quite high isentropic efficiency of turbines, and let's say if you really aim for electricity production at larger scale with condensing turbine, you could have efficiency running from let's say roughly 15 to 35% maximum efficiency, and that's very much depending on system scale. Say this 15% could be quite typical for let's say 1 megawatt scale, and 35% would be more typical for, let's say roughly 100 megawatts. As turbines are usually designed for continuous higher loading rates, applications, their efficiency is usually expressed at higher loading rates, let's say above 50%. Now looking at gasifiers, as indicated, the gasifier itself typically has an efficiency between 60 and 80%. Part of this is also because the gas coming from the gasifier is hot, and it still needs to be cooled down before it can be used in a combustion engine. So, for example, if you would have a gasifier that would fuel a boiler system, for example, where there's not so much a need for cooling down the gas, then the efficiency, the overall efficiency could be higher. Typical generator efficiencies, as indicated, are roughly between 25 and 40%. Overall efficiency, which you would normally find, is between 15 and 25%, although some systems could be higher or lower still. And because of the high dependency of the actual efficiency of combustion engines to loading rates, the overall efficiency drops at reduced system loading rates. For biogas systems, anaerobic digestion, as indicated, the digester output depends on the feedstock properties, and also, let's say, to the digester design. Let's say, assuming a correct design, you could have a sufficient digester size to have more or less complete conversion of feedstock to biogas. So then you look at generator efficiency, and similar to what you would find in gasification systems, you would end up somewhere between 25 and 40% maximum. And here also you'll be faced with efficiency drops at lower system loading rates. Some indicative maximum values, which can be used in say in first assessments of systems. Well, the biogas generator sets is indicated, let's say, roughly 25 to 40. Larger systems could go to 42, 43%. That would be really high-end combustion systems. Gasification systems overall would be a bit lower because of the efficiency of the gasifier, the gasification conversion step. Looking at condensing turbines, for combination with combustion, you would get from, say, 15% or a bit lower. You will go below the 1 megawatt scale, and then up to, say, roughly 35% for if you go towards the 100 megawatts scale. And steam engine would be in the lower efficiency range, typically, so between 5 and 10%. Then, as indicated, when you operate systems at lower loading rates, you may get lower actual efficiencies, especially for internal combustion systems. This can really make a very big difference if you load your system below 50% load. For steam engines, this is more pronounced if you go below, let's say, 30 to 40% of its rated capacity. this is really something to take into consideration when choosing a certain generator size for the system. I've seen quite some farm scale biogas systems in Asia, for example. It's quite common for farmers that have certain wastewater treatment systems, covered lagoons that produce biogas. There's a strong tendency to choose a conversion, let's say a generator scale that is, let's say, 3 times more than the maximum electricity demand at the farm. And that means that such systems could be running at let's say roughly 30% of their capacity. So let's say their efficiency would only be a fraction of the maximum. We should stress that the efficiency here are relative to the maximum. So it's not like these systems, these points are running at 100% efficiency, but they are running at, let's say, 100% of their maximum efficiency, which could be, for example, between 25 and 40% of a biogas generator. So, for example, if you would have a 500 kilowatts biogas generator that could have a maximum efficiency of, let's say, 33%, then if it's well loaded, let's say 90 to 100%, then you could actually get 100% of this 33%. But if you run it at only 25% of its capacity, so it could be, let's say, for 500 kilowatt systems would be 125 kilowatts, then the efficiency would be only, let's say, 35 to 40% of this maximum efficiency. So that would mean that it would be running at 12, 13, 14% overall efficiency. I have some exercises later that show this as well. I think I'll drop some of the examples because we're starting to run a bit into time constraints, I think. Maybe this could be interesting. If we would look at the gasification system for captive power, so let's say an isolated situation, not grid connected. For example, a coconut shell gasifier. And we look at the occurring loads, let's say the electricity demand, which could be varying between 75 and 140 kilowatts, with, for example, 100 kilowatt average. You could say that the minimum capacity required could be expressed as a percentage of the maximum load. For example, if we want to have it we want to have at least 20% overcapacity in case of load peaks, then you would say you need a system with a minimum capacity of 175 kilowatts. If you would say, well, I want to have it running at more than 30% of its capacity, then you would say, well, it says here 80 kilowatts, it should be 75 kilowatts divided by this minimum loading rate. Then you could say the maximum capacity would be 250 kilowatts, because if you would have it bigger then the loading rate would drop below 30% in the let's say low demand situation. Now, if you would select a capacity of 175 kilowatts, or let's say the nearest available capacity, based on the maximum capacity, the maximum current loads, then you could have an average loading rate of, let's say, 100 kilowatts, which is the average load, divided by 175 kilowatts, which would be the system capacity. It would be, let's say, 57%. If you have 57% for a gasifier of, let's say, 175 kilowatts, then you are, let's say, at roughly 18 to 90% of maximum overall efficiency. However, if you're operating it at let's say 57%, which would be roughly here, then you could say that you have an actual efficiency which is somewhat below the maximum efficiency. You could run it at, let's say, 80 to 85% of of this 18 or 19%. That means that the overall actual efficiency you would find is, let's say, roughly 15%. Now, at 15%, you could find a biomass consumption of, let's say, 160 kilograms per hour on average. On the other hand, if you would go with a larger capacity, let's say you would go for 250 kilowatts, which would be, let's say, the high end of the appropriate scale range, and you'd get a lower average loading rate. The average load would be about 100 kilowatts. System capacity at 250 kilowatts would be 40%, and that means that even though, say, you have a somewhat larger system, so you might have a somewhat higher overall efficiency of, let's say, 90 to 20%, but you're running it at only 40% of its capacity. So that means that, you know, this actual efficiency really starts to decrease the actual efficiency. And in this case, you could have, say, 60 to 65% of its total, of its maximum efficiency, and that means that it could be as low as, let's say, 12% overall average efficiency. And that means in such a case, for such a larger system, the actual biomass consumption could be substantially higher. Say, for example, in this case, 200 kilograms per hour, in comparison to when a smaller system would have been chosen. So that is, let's say, the point where scale and efficiency and biomass consumption more or less come together. So you have to find a correct choice between these different considerations, and that's not always a very easy thing to do. I don't know if there's any questions about this.
60% full, 45.
No one? Okay, then we continue. So let's have a look at some system components that you can find in different types of bioenergy systems. First of all, steam boilers. The capacity is usually expressed as in megawatts. Some cases for smaller boilers, and you can also have kilowatts. Or you could have, let's say, have them a capacity expressed as their steam production capacity in tons per hour, sometimes kilograms per hour, and then it's typical also to denote the steam conditions, so the pressure and or temperature of the steam, or whether it's a saturated steam or let's say superheated steam. Calculations on the boiler capacity, for example, in megawatts, are done, say, on the basis of the enthalpy of the steam and the feed water. Let's say the difference between the steam enthalpy and the feed water enthalpy, both in kilojoules per kilogram, and the steam flow. Both of them can be used for calculating the boiler capacity. So the difference between in the enthalpy multiplied by the steam flow, and then divided by the conversion factor of kilojoules to megawatt hours, will give you the capacity of a boiler in megawatts. Small example: if you would have, for example, a steam system with condensing steam turbine, which has a boiler producing, let's say, 38 tons per hour of steam at a pressure of 65 bars and a temperature of 480 degrees centigrade. And you have certain conditions for the feed water, return temperature. Then you can calculate using either steam tables, from which you can find the enthalpy of the high pressure steam, or the let's say the feed water. Coming back to the boiler, and you have the steam flow, so you can calculate the boiler power as 32.8 megawatts in this case. And looking at biogas systems, for example, it's a bit different, as indicated, because you're looking at the conversion capacity of a digester. You're looking at biological processes, which on the one hand take time. Usually the conversion of biodegradable material to methane to biogas takes days. If you look at a batch system, for example, batch conversion. On the other hand, a digester can have let's say a limited capacity, a limited volumetric capacity to convert organic matter to methane, and both factors are required to to calculate a certain minimum digester capacity. So on one hand, you can look at the amount of feedstock that you feed to a system, the amount of time, which we call the hydraulic retention time, that is needed for conversion of the feedstock to gas. Well, then there's not just the time required for the conversion of the feedstock, but you also have a minimum time that the feedstock needs to be in the digester in order to avoid the so-called washout of bacteria. Let's say the multiplication of new bacteria takes time, depending on the type of bacteria and the different stages of the digestion process. And especially the bacteria that produce the methane have an average multiplication time of at least 10 days, depending on the digestive temperature. So let's say lower temperature digesters could even have longer multiplication times, and that means that the minimum hydraulic retention time could even be higher. So that's on one hand. On the other hand, on the basis of the maximum organic loading rate, that means the amount of organic matter that you add per cubic meter of digester capacity. There are certain conversion capacities of digesters, also temperature dependent. And if you increase the feeding rate above this maximum organic loading rate, then you may at some point get unstable situations due to you would say overfeeding of bacteria. So let's say the production of some of the bacteria might speed up, so that, for example, organic acids can build up, and other bacteria that don't have the same conversion capacity may not be able to keep up with the conversion of these acids to other building blocks of the biogas. And that means that in this case, for example, because the acid build up, you get a drop in the pH in the digester. That may in turn lead to problems with certain bacteria strains, and it could eventually deteriorate, get an unstable system, and you might end up with a process that will stop entirely. Now, for let's say general digesters, let's say stirred and heated digesters, you might get typical organic loading rates of about up to 3 kilograms of volatile solids, let's say organic dry matter, per cubic meter per day, and it can be higher than this for highly optimized systems, but this maximum loading rate of 3 is quite a typical high range value. So it means if you want to look at the maximum, the minimum volume of digester, you'll be looking on the one hand about to the minimum hydraulic retention time multiplied by the feed rate. On the one hand. On the other hand, you could be looking at the total amount of organic dry matter that's feeding to the digester in relation to the maximum rate of this digester. and you know the higher one of these two will set the minimum value of the digester. Then, in addition to the digester conversion capacity related to its volume, you may have a certain need for storage of biogas, and that could be quite a limited amount if you have a continuous usage of biogas. For example, if you have a grid-connected system that is running continuously at a continuous loading rate, then you could have make do with a relatively low amount of storage. On the other hand, if you have, let's say, discontinuous consumption, for example, systems that run only for a certain period in a day, then your storage depends on the time between the shutdown and the restart of your gas utilization. And the extra storage that you select can also depend on the potential returns that you may expect from, let's say, a larger storage. So let's say if you have, for example, a system in which you have longer shutdowns, and you want to store all the gas that is being produced during this stop. It means that you will be able to use this gas once the generator is running. So you will have higher returns. On the other hand, it will mean that you have a larger storage, and that will come at a certain cost. So it will be let's say an economic consideration whether this is worth the additional investment. I think I'll skip the example for now, because I think we're only 5 minutes to 11. I hope that you're all able to follow these calculations if needed, and if you find that that's something is lacking, or when you have any questions, please don't hesitate to drop me a line. I can give some further explanations if needed. Forwards to generate capacity calculations for biogas systems. Typically base them on let's say the maximum biogas production rate in let's say cubic meters per day, in combination with the number of operating hours of a generator, so the hours per day, and say the two combine into a certain hourly gas consumption of your generator, and in combination with the methane content of the gas, which is the main determinant of the value of the methane, or of the biogas, and the generator efficiency, which is also dependent on the loading rate, will give you an indication of the appropriate generator capacity using this formula. Also have a example of this following this method. Again, here please please have a look at it and let me know if it's clear or whether you have any questions about this. Other system components that you may want to look at the scale could be biomass pretreatment systems, for example, when looking at biomass that needs chipping, for example, in order to reduce the size, either for automatic boiler feeding or for gasifier systems. You typically look at the minimum throughput of such systems, which could depend on say the average, or let's say the total biomass intake over certain periods. For example, over a week, divided by the number of hours per week that you want to run the system, or the chipper, and then you get a certain minimum capacity, and you may want to choose somewhat higher capacity if you need some further flexibility for using the system. A little example for steam power plants consuming say roughly 1,700 tons per week of wood chips. Now, if you have a wood chipper running for 5 days per week for one shift, so say roughly 40 hours per week, then the minimum capacity of the plant would be 42 hours, 42 tons per hour. Biomass storage is very important, especially for systems that have a large requirement of on-site storage. You may find, especially power plants that depend on irregular fuel supply from outside. They need to have a certain storage in order to maintain operation, and to make sure that there's always sufficient biomass fuel available for continuous operation. Think of, let's say, infrastructural problems of fuel supply from external sources due to rainy season problems with road accessibility. You can also think of say seasonal availability of biomass, for example, from certain certain industries that convert primary products to secondary products. So let's say agro-processing industries producing byproducts and waste used for energy production. Now the storage volume that must be considered is dependent, of course, on the basis of the quantities and the amounts that need to be stored, and in combination with the bulk density of the fuel. So let's say if you have fuels with a low bulk density, like in terms of byproducts, shells and husk, but also wood chips can have limited bulk densities. So it means that every ton of fuel that you need can have multiple in terms of cubic meters that need to be considered for storage. And then you may have a maximum stocking height, and that will determine how much space is needed for the storage of the biomass. Another example, I think we should be stopping here. we can pick up during the next session and take the last bit of this session, which is more on let's say the space requirements of different types of systems. Carlos, what do you think?
No, I fully agree. We may stop here, really.
Mm-hmm.
Yeah. And then the next session, you will continue from here, probably.
Okay, well, thank you everyone for your participation today. I should add we've been discussing within the team the possibility of gathering some specific questions from each of the participants. Questions about the training matter, the training materials, whether that is from the bioenergy or the solar or the hydro training sessions. So it can be very specific questions about something that was unclear or something that's you found that may have been omitted in the training sessions. It can also be something that you may have encountered in projects that you're working on. For example, some of the studies. I know there was some exchange between one of the participants and Dr. Arans, just the solar trainings, on one particular case study in Mozambique. We would like to ask you to submit some questions and cases, and we are thinking of organizing let's say a central session including all of the trainers, and maybe get some discussion between the participants asking the questions and presenting the cases, and then let's say on the other hand the trainers, so that we can address some issues that you are facing yourself. We will be circulating some let's say a document in which you can indicate the questions or the cases that you'd like to have discussed, and we will do that in the course of this week. And then hopefully by the end of next week we will have all the questions and cases collected. We can make some selection of what we can discuss in this joint session. So I will get back to you on that. Secondly, I've prepared a case study document which will send after this session to you, describing a case at a cashew processing facility that produces byproducts, say waste of the cashew shell, and attached some questions, some basic questions on what could be an appropriate type of technology, what could be an appropriate scale. That's the kind of questions that we've been looking at during this session. And this the same case we could be using in follow-up sessions about say further assessments, for example, on the financial aspects of such a project. I will be sending that to all of the participants, and I'd like to ask you if you can have a brief look at it and provide some answers by the next session. I will explain that also in my email message.